This is the last lecture for Escape from Scientific Absurdity 2024. ESA28H, Symmetry and Conservation. So we have shown that the physical path of a particle with mass m under conservative force, that is described by the potential energy minus the gradient of the corresponding potential energy, is delta S equals to 0. Delta S means the variation of the action, that is the time integral of the Lagrangian integrated over a time interval with the initial and final position kept to be the same as the physical one. And in case we vary the path from TA to TB to be unphysical, keeping delta x TA and delta x TB is 0, except that everywhere else can be modified from the physical value. In that case, the action is minimized as long as the deviation has been made from the physical path. Here, the action is the time integral of the Lagrangian, and the Lagrangian is the kinetic energy subtracted by the potential energy. In non-relativistic case, the kinetic energy is 1/2 mass times the velocity squared. In case we study relativistic case, we have to modify this kinetic energy, but that is out of the scope of this course, so let us restrict ourselves to the non-relativistic case only. Using this extremum condition for the action, we can reproduce Newton's second law of motion. This method is called the calculus of variation, developed by Euler and Lagrange. And the corresponding equation of motion coming out of this action condition is called Euler-Lagrange equation. For convenience, we restrict ourselves to the velocity-independent potential energy. In fact, if we consider the electromagnetic case, a magnetic force forces the potential energy to be dependent of the velocity, because Lorentz force is electric charge, velocity, cross product with the magnetic field. Because of this, the potential energy must be dependent upon the velocity. However, it is a little bit extremely complicated for us to study at the moment. It will be postponed until we study relativity and electromagnetism. So, delta S is the time integral of the variation of the Lagrangian, and the Lagrangian is varied by varying the physical path to physical path plus varied path. As I already stated, the endpoint condition restricts the variation. So it is it is not allowed to vary the endpoints, the starting and end points. In this variation, wait a second, there is a typo. This is not delta, it should be removed. Delta L is L evaluated along the path, buried path, and subtracted by the Lagrangian evaluated along the path, the physical path. The variation of the Lagrangian is because Lagrangian is kinetic energy subtracted by the potential energy. Variation can be made in this manner. We again can make use of Leibniz rule to find out the variation, but in a simpler manner, the purely mathematical way, we can make use of the fact it is depending on the velocity along the Cartesian components x1 dot, x2 dot, and x3 dot. Okay, so because the kinetic energy is a function of three variables, we can make use of the chain rule to find out the variation of the kinetic energy. The explicit computation of the variation of the kinetic energy can be made by substituting the explicit values for the partial derivative of the kinetic energy with respect to the each Cartesian component of the velocity. The results are given here. As a result, if we substitute these results in here, we end up the fact we find, wait a second, 1/2 m, and derivative is 2 times x1 dot. Therefore, 2 cancel, so we have to remove this factor of 2, and factor of 2. Note that x1 dot squared, x1 dot equals 2x1 dot, and so on. All right. As a result, the variation of the kinetic energy is given like this. This is a scalar product of the linear momentum and the variation of the velocity. We can do the same job for the variation of the potential energy. This is not 1/2 mv squared. This is a potential energy. So, in a similar manner, the variation for this potential energy, in case the potential energy is independent of velocity, it should be evaluated in such a manner by applying the chain rule. We know they are the Cartesian components of the gradient of the potential energy, and finally, this expression can be expressed as the scalar product of the variation vector and the gradient of the potential energy. We notice that the velocity-dependent term does not appear in this expression. We copy these two results and substitute it to the variation of the Lagrangian. The variation of the Lagrangian is a variation of the potential energy subtracted by the variation of the kinetic energy subtracted by the variation of the potential energy. We copy these results in here, substitute them for delta t and delta v. We find it here. As I told you, mass times velocity is the linear momentum of the particle. Minus gradient v appears here. The linear momentum of the particle can also be expressed as the partial derivative of the kinetic energy with respect to each Cartesian component. Because the potential energy is assumed to be independent of the velocity, kinetic energy minus potential energy, velocity dependent term does not appear, so this guy is 0. Therefore, it is the derivative, partial derivative with respect to the velocity is the same for both kinetic energy and the Lagrangian. As a result, we have additional condition. The gradient of the potential and kinetic energy is also 0. It is true only for the Cartesian coordinate system. The Cartesian coordinate system, kinetic energy does not depend on the Cartesian coordinate. Instead, it's the velocity only. All right. Therefore, gradient of the potential energy is 0 vector. As a result, the gradient of potential is gradient of the potential energy is identical to the gradient of the Lagrangian multiplied by the negative sign. You know, Lagrangian is kinetic energy subtracted by potential energy, and gradient of T, kinetic energy, vanishes. We have minus the gradient of potential energy. Therefore, we obtain this. As a result, the variation of the action is the time integral over the same time interval of the integrand, that is the variation of the kinetic energy subtracted by variation of the potential energy. We remember the variation of the kinetic energy. Variation of the kinetic energy is this. Linear momentum, scalar product, velocity, the variation of the velocity. Next term, this guy minus potential energy is replaced with plus the Lagrangian's gradient. All right, what about the first term in the integrand, p dot, variation of the velocity? We can assume that this is, because this is x dot is delta, this, and they commute. As a result, we can expect that this term comes from the expansion of this. Therefore, we have to subtract the unnecessary term that is contained in it, that is the derivative of the first factor. As a result, this one, the first term in this integrand, should be replaced with the total derivative subtracted by this time derivative of linear momentum. That is nothing but the force. Therefore, the variation of the action, the same, and we have replaced this guy with these two terms. And we find that the total time derivative integrated over TATB, because the endpoint there is no variation, this integrand does not contribute to the integral at all. So this disappears. Finally, what we have for the delta S is we have a common factor, scalar product with a variation. And the vector that is multiplied to delta x is gradient Lagrangian minus force. That is a linear momentum's time derivative. Now we have found that this delta S must be 0 to order delta for any arbitrary variation that keeps the endpoint the same. That is possible if and only if this vector inside the brackets must be zero vector. That is called Euler-Lagrange equation. And actually, if I pull out component, Cartesian component, the gradient, ith component of gradient is nothing but the partial derivative with respect to the ith Cartesian coordinate. So this one is replaced with this, and this one is time derivative. And what is the linear momentum P? What we already have seen is that linear momentum is linear momentum is a gradient of Lagrangian. Okay? Gradient of Lagrangian? No, gradient, not a gradient. It is a partial derivative of the Lagrangian with respect to the velocity. Okay. So finally, this ith Cartesian component of the linear momentum is a Lagrangian's partial derivative with respect to the ith component of the velocity. This is called the Euler-Lagrange equation, and this notation that represents the linear momentum is called conjugate momentum. The momentum conjugate to the coordinate xi. So linear momentum pi and xi, they are correlated as a pair. That's the reason why we use conjugate. An important point of this Euler-Lagrange equation is, first of all, it reproduces Newton's second law. It is identical to the Newton's second law. In addition, this is nothing but the time derivative of linear momentum that is a force. But we find that this guy, if the Lagrangian is free of any coordinate, then it's a partial derivative with respect to a single coordinate is a zero. That indicates that the corresponding conjugate momentum's time derivative is zero. That means linear momentum, actually the conjugate momentum that is correlated with corresponding coordinate is constant because pi dot equals 0. That is the result for the symmetry coming from, natural symmetry coming from the Lagrangian mechanics. Okay, if you are interested in more formal structure of classical mechanics, why don't you study further the intellectual beauties series that will be given from next semester. Thank you very much for listening all 28 lectures for Escape from Scientific Absurdity. Thank you very much.